Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at National College of Ireland. And I've been asked to do this particular live stream today, and in particular, I've been asked by some of our students here if I would cover analysis of variance. Um, so that's what I'm going to do today. Is I'm going to concentrate on, let's say, in this, it's hypothesis testing, and in particular, the concept or the technique known as analysis of variance. Okay, that's what I'm going to concentrate on there today. I just wanted to just see who we've got. I have one person there present, so maybe I'll just check to make sure that they can hear what I'm actually saying and that they can actually see the screen. Okay, so I'll just say hi there, hi there. Uh, can you hear the cast? All right. Can you hear me? Okay. So that's a question I'm just sending out there, just to make sure that that the 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 audio is clear enough. And then just in relation, I suppose, to the video, uh, can you see the the video? The video. Okay. Looks a little bit hazy here on my screen. But maybe that one person that's listening there will be able to tell me whether they can see uh, and here. I'm just actually going to try to hit the focus button here, just the autofocus button, just to see how I get on here, just with my focusing, and hopefully that comes in. Ah, there we go. I think that's probably a little bit better now. Okay, that's a bit better focused. Okay, sure. And anyway, what I'm going to do is I'm just going to continue on with this concept. So let me just maybe just go over the logic of analysis of variance. Uh, so the logic of analysis of variance. Now we know when it comes to a two sample case, okay, when we have two groups, so let's say the two group case, that effectively what we're doing is we're comparing the two distributions. Okay, so the distribution for group one, let's say here's group one, and the distribution for group two, and we're probably doing a t-test. Okay, but effectively what's going to happen is the t-test is effectively going to measure the distance. Okay, it's basically going to measure the distance between the two distributions. Okay, and it does that through its formula. Actually, if you look at the formula for the t-test, it says that t is equal to, let's say, the independent samples test, it's x1 bar minus x2 bar minus mu1 minus mu2, all over, let's say the variances are equal, sp squared over n1 plus sp squared over n2, the pool variance, and it's the square root of that. But effectively, what we actually have here is we have distance measures. Yeah, the distance between the two distributions under the null hypothesis. There you go. Okay, that's a distance measure there, subtraction. This is the distance between the two pieces of evidence. Okay, and this is the distance between the distance of the evidence, what we expect in the null position, the distance between the null difference and the distance between the evidence distance. So effectively all standardized. Yeah, effectively the t distribution is calculating the distance. Okay, the t statistic. So that seems straightforward enough. When we have two distributions, it's easy enough to calculate these particular distances. Okay, but I suppose what happens when we have more distributions? Well, I suppose when there's more than two groups. Okay, uh, well, I suppose the naive okay approach would be, okay, we're trying to find out whether there's differences between the groups. Well, why not conduct t-tests? Okay, that's something we could do. But remember that every t-test has a type 1 error rate. Okay, so every time you conduct a t-test, there's a probability of you committing a type 1 error. And the more t-tests you undertake, yeah, that error is going to actually explode. Okay? I'm going to actually have a look at that later on in relation to actually, to just so that we can actually visualize actually what the error is and why t-tests won't work and t-testing different groups won't work. So let's have a look at a different approach, this analysis of variance approach. Okay, the analysis of variance. And what does it do, the analysis of variance? So effectively, let's just assume we've got three groups. It doesn't have to be three. We could have four groups. We could have five groups and so on. But let's just assume that we have three groups. And what I'm going to do is I'm just going to draw their distributions. So let's say the first group is positioned here. That's its mean value. Let's just say that this is the first group. And let's say the second group is positioned here. So there you go. There's the second group. Okay. And let's say, for argument's sake, that the third group is positioned out here. Okay. So let's say there's the tour group. And they have different standard deviations, and there's different numbers of observations associated with each of them groups. But effectively, they all have a center point. Okay? So how the hell do we capture, let's call this group A, this group B, and this group C. So how do we calculate, how do we measure distance? Yeah, okay. Because in the t-test situation, yeah, there's two things at play. There's the distance and there's the standard deviation. Okay? But in the t-test situation, when we're measuring how far the two distributions are apart, yeah, we take into consideration these distances and the standard deviation. Right? So how the hell are we going to measure the distances here? And I said we could compare group A to group B, group A to group C, and group B to group C. We could make them comparisons with t-tests, but there is a problem with that. Okay? So what we're going to do is this, and this is this little bit of, let's say, the sleight of hand that we're going to do, is we're going to make two measurements of distances. Okay, so we're going to, sorry, I'm just throwing my keys up there. We're going to make two measurements of distances. The first thing we're going to do is this, is we're going to take all the observations in group A, all the observations in group B, and all the observations in group C. And if there's more groups, all of them other observations. We're going to take all the observations and we're going to throw them all in together into a new bag, let's say. Yeah. So all the observations go into a new bag. And effectively what we end up with is we end up with a new distribution. Okay? So we end up with a new distribution. I don't know where it is, but it's going to contain all the observations. I'll just draw it in here. Okay. So we end up with some new global distribution. Okay. So this is a global distribution, okay, of all the values. Okay. So now what we can do is we can measure distances. Yeah. Okay. We can measure the distance that our individual groups are away from this global distribution, and importantly, the center of the global distribution. So we could measure how far this distance is away, that distribution, okay, its center, from this center. We could measure how far this distance is away from its center, and we can measure how far this distribution is away from its center, from the center of the global distribution. So what this now gives us, yeah, is this gives us an idea, yeah. And let's say we calculate the average of them distances. So now we have this concept of the average distance that the centers of our distributions are away from this global center position, if that makes sense. Okay. So effectively what we're doing here is this, is let's just do some maths, yeah, is that each one of our groups has a mean value. Okay. And when we throw all the groups in, when we throw all the observations in together, we end up with another mean value, which is this global mean value. Okay. So what we're going to do is we're going to calculate the distance that the individual group means are away from this global mean. Okay. So we're going to calculate the distance. Yeah. And we're going to do this for them all, if that makes sense. Okay. Well, hang on. We don't just calculate, because distance is over here going to be negative and distance is over here going to be positive. What we actually do is we always calculate the square distances. Isn't that right? Okay. And we need to do that for all the groups. But let's keep in mind that some of the groups have different weightings. And what I mean by that is some of the groups have more observations than other groups. So what we need to take into consideration is how many observations are in the individual groups. Okay. So you can see now what we have is we have this measure here. And we need to add that up we need to do this calculation for each one of our groups. So what I'm going to say is we're going to do that calculation for each one of our individual groups, okay, that are elements of the global group. Okay. So basically what we now have is a sum of squares. And what we're going to do is we're going to divide that by, okay, we're going to divide it by how many groups we have. Let's call that K. And we reduce it by 1. Okay, this is the degrees of freedom. Okay, so this is a variance calculation here, if that makes sense. It's a sum of squared distances, yeah, and it's the average sum of squared distances. So this is now a distance measure. And what is this? Well, this measure here is the distance, okay? This measure here is the distance that our group means are away from the global mean. So effectively what we now have is this is a measure of the distance between the actual individual distributions. So actually what we're going to call this is an average sum of squares. So it's a sum of squares, a mean sum of squares, and it's a mean sum of squares for the between distance between our distributions, between our individual distributions and the global distribution. So we're going to call this our between measure. So now we have a measure of how far the distribution centers are on average apart from each other. And the way we're measuring that apart from each other is apart from this baseline value of this global mean value, which is just all the observations added together divided by how many there are. Okay, so that's one measure of dispersion we have. Okay, now what we can do is that we can look at the individual distributions. Okay, the individual distributions, and we can calculate how skinny they are. In other words, we can calculate them variances, yeah? For group A, we can calculate its variance. We can also calculate the variance for group B, and we can calculate the variance for group C. Mathematically, what we're effectively doing is for each observation in a group, we're going to take away the group mean, okay? And we're going to square it. And effectively what this is the square distance that individual observations are away from their own mean. It's a variance, okay? It's a measure of skinniness, yeah? Okay? But let's keep in mind that we're going to do that for all of our distributions, okay? So for all of our groups, okay? So all of our small groups in this big group, okay? There's a certain number of them, and we're going to average them, okay? Well, how do we average them? Well, it's the total number of observations that we have in the global group minus the number of groups we have. This is the degrees of freedom. But effectively, what we've measured here, okay, is how skinny how skinny on average, how far the individual observations are away from their own group and their own mean value, okay? uh, which is a measure of variance, which is a measure of skinniness of the distributions. So this is measuring within each distribution, within the distributions themselves, just concentrating within the distribution. We take the mean away from each individual value and we square the distance, and we do that for all of them, yeah? So actually what we end up with here, this is a sum of square distances. So once again, this is a sum of squares. We're dividing by how many things we have. Well, we're compensating for the number of groups, okay? So this is effectively an average. So this is a mean sum of squares, but this is a mean sum of squares for within, okay? So with respect to this analysis of variance, okay, what the analysis of variance now basically boils down to is two measures, yeah, two measures. One measure of how far the distributions are apart on average, and another measure of how skinny on average the distributions are, okay? Which now allows us to bring these two ratios together, so these two values together to create a ratio. So now what we end up with is our test statistic, okay? And this is why this is called an analysis of variance, because there's variances being calculated in both cases. But you can see logically, hopefully you can see logically, that by concentrating on these two different ways of measuring variance, okay, effectively what we're asking is, the question is, how far are the centers of the distributions apart from each other, okay? So now our test statistic, this is called an F statistic, and it's equal to the mean sum of squares between the mean sum of squares between measure, okay? That's how far the distribution centers are apart on average, divided by the mean sum of squares within measure. That's how skinny the distributions are on average, okay? And let's just consider this here for a moment, okay? So what we might have, okay, so we're just going to consider this mean sum of squares for one moment. I am going to do a calculation on how to do this particular test now in a few moments. So we have our F statistic, which is the mean sum of squares between divided by the mean sum of squares within. Let's concentrate on this, yeah? So the top bit is how far the distributions are, centers are apart on average, and the bottom bit is how skinny they are, okay? So let's think about this. If this is large here, if this is a large number, okay, let's just see what's happening, yeah? So if the mean sum of squares between is a large number, what it means is that on average, the distributions are far apart. So we'll just say that that's what it looks like when they're far apart, okay? And then we have two different types of cases. The within measures, let's say, no, this is large, okay? So our MSSB is large, okay? And now we have two cases for the MSSW, okay? Well, let's assume it's small. Small meaning the distributions are skinny, okay? Small meaning that the distributions are skinny, okay, on average, which means that there's going to be at least, sorry about that, my I don't know what that is yet. That was my speaker there, or some message coming in there. Yeah. So that's going to be the mean sum of squares within, when they're on average they're skinny. It basically means that they're far apart and they're skinny, which means there's not going to be much overlap between them. And hence, we're going to deduce, or we're going to infer from that one of the groups must be different to the other groups. Okay. The other possibility is that MSSB is large. The centers are still well apart, but MSSW is also large. Yeah. Okay. And what happens then? Well, if MSSW is large, it means that the variance, the within measure is large, which means that the force distribution probably is like this, has a big variance. The second distribution probably like this, has a big variance. And the third distribution even has a bigger variance. Okay. If that makes sense. Effectively, what I'm saying is that there's loads of shared area between these distributions. Yeah. Okay. So this effectively is this. If this is large and this is small, the F statistic is big. If this is large and if this is large, the F statistic, well, it's closer to 1 because both of them are large. Okay. Then the other thing that could happen is, I suppose we have the other possibility that the between measure, okay, that the between measure is small, which means that the distributions are very close to each other. Okay. They're very close to each other. But now the within measure could also be small, which means that it means that they still don't share much area, if that makes sense. So they can still be close together on average, but they're really, really skinny. Okay, which means that they're different. Okay, and the other possibility is that they're close together, but that their variances are big. Okay, okay, their variances are big. Okay, which means that the share loads are various, so there's no difference. So it is possible still to have a small mean sum of squares between, which means that the averages are close to each other, small effect. Okay, but that the variances are very, very small, which means that the F statistic is also going to be large. Okay, so they're the 4 scenarios in relation to the F statistic. A big F means that there's a difference. A small F means that there is no difference between them. Okay, so just maybe guys, I have 10 people there. I hope this is all going well for you. Just maybe now, just to come back to this logic, there's one thing I did say I was going to cover before I do the actual calculation. Okay, well, the question is okay, so we have this technique now, this ANOVA, that allows us to figure out using this F statistic whether there is evidence to suggest that there's a difference between the averages of our groups. Okay, we don't have to have 3 groups, we have more than 3 groups. But I said that earlier on. Well, why the hell don't we just use t-tests? Why don't we just compare group A to group B? Should we know how to work a t-test? Group A to group C and group B to group C. And if we reject in any of them cases, we know we found specific differences. Yeah. Now, the thing about the analysis of variances is that when we do the test, we set the type 1 error rate at the very start of the test. Yeah. So it has an alpha value. Okay. So we've only got one alpha associated with this test, but with each one of these, we have a specific alpha. So let's consider that in a little bit more detail. Okay. So let's assume so we're considering now, t-tests and the type 1 error rate. Okay. So let's assume we've 3 groups. Assume we've 3 groups. 3 groups. And I suppose, excuse me. So we've got 3 groups. How many ways can you select 2 objects from 3 groups? Well, there's 3 ways to do it. You can compare group, as I said, you can compare group A to group B, group A to group C, and group B to group C. Okay. That's our 3 ways to make the comparisons to see whether there's differences from a paired perspective. Okay. Let's assume that we do t-tests for each one of them. Okay, a t-test for each one. And for each t-test, we set the alpha rate at the probability of committing a type 1 error. Let's say we set it at alpha. And let's say we could choose 5%, 0.05, 0.05, 0.05. Okay. So I'm after doing these 3 tests. Okay. So I want to know what's the probability. Okay. The question I want to know is what's the probability that I commit a type 1 error. Think about it. I could commit it here or here or here. So there's many different ways I could commit it here and here. I could commit it here and here. I could commit it here and here. There's lots of different ways I could commit a type 1 error. Yeah. But let's change this. Let's ask the question: what's the probability of committing no error? What does that mean? Okay. So it means that when I did the first test, let's say test T1, T2, T3, when I did T1, Okay, so that's the probability of no error means that I have to calculate the probability that there was T1 had that there was just no error for T1, and there was no error committed for T2, and no error was committed for T3, if that makes sense. Okay? If I want to calculate what's the probability after I do all these tests that I don't commit any error, well, then for me not to commit any error, okay, I mustn't commit an error with the test 1, and there mustn't be one with the test 2, and there mustn't be one with the test 3. Now, these are all independent of each other, so hence we have this the product of the individual probabilities. So it's P times no error for T1 times the probability of no error for T2 times the probability of no error for T3. Okay, but hang on, the probability of committing an error is 5%, so the probability of no error must be 1 minus 5 or 1 minus alpha. Okay, whatever the alpha is. So that probability is 1 minus alpha. This probability is 1 minus alpha. And this probability here is 1 minus alpha, which is effectively 1 minus alpha raised to the power of 3. Okay, so this is the probability of committing no type 1 error, okay, across the 3 groups, which means that the probability of committing a type 1 error, okay, must be equal to 1 minus the probability of no error, which is 1 minus alpha over 3. And what does that give us? When it's 5% in the 5% example, okay, the 5% example, we have the probability of no type 1 error, okay, after we do 3 tests, okay, or sorry, the probability of committing a type 1 error is the probability of a type 1 is equal to 1 minus 0.05 raised to the 3. And where the hell are my calculators? My calculators are over here somewhere. Here's one here. So what I have is 1 minus 0.05 is 0.95 raised to the power of 3. Okay, give us that value here. And I have to take that away from 1. So what's that? That's equal to 0.8573. Okay, so let me just turn this page over. Nearly ready, guys, to do an example of this. I just wanted to get that type 1 error rate out of the way. So what we now have is the probability of a T1 error, type 1 error, is equal to 1 minus, and here we have, 0.1 minus 0.857375, which gives us, if I just take 1 away from that and then just change my sign, gives me 0.142625. So actually, by doing 3 individual t-tests, even though we set the individual error rates at 5%, the probability of actually making an error across that particular, let's say, experiment-wide, across the whole set of tests, actually explodes up to 14%. Okay, if we have another group, let's say we had 4 groups, okay, well, you could compare group A to group B, group A to group C, group A to group D. You could compare group B to group C, group B to group D. You could compare C to group D. Okay. How many ways can you select 2 objects from 4? Is 4C2, 4 second function C2 gives us, there should be 6 ways, 2, 4, 6. Okay. So the error rate now explodes, the probability of a T1 error, okay, when there's 4 groups, and if you did all individual t-tests, alpha is equal to 0.05, okay, for them all, okay, well, then it becomes 1 minus 0.05 raised to the power of, this case, is 6 groups, okay. What does that give us? Well, 1 minus 0.05 is 0.95. Raise that to the power of 6 gives us 0.735. I'm just going to take 1 away from and just change the sign, which gives us now, we're up to 0.26%. 26% chance, for 4 groups if you did individual t-tests. The point I'm trying to make here is this, is that doing individual t-tests is a very naive way of trying to find a difference between groups when you have many groups. So what we'll do is we'll do this ANOVA, this analysis of variance, allows us to control for that particular rate of committing type 1 probabilities. Okay? Okay, guys, I hope that that's at the helping there, just in relation to setting the scene, in relation to, sorry, I just want to get, this is annoying me here, just this little page hanging over here. Whoops, Daisy, there we go. Right? So hopefully that's setting the scene for us just in relation to this analysis of variance. Just to recap what I've gone through at this particular stage, and you can always rewind this video later on. I've put forward the argument and the logic behind the t-test and why the t-test is effectively a distance measure that's standardized. So it's effectively measuring the distance between two distributions with respect to a standard meter stick. Okay. The analysis of variance measures two measures of distances. Using variance measures how far the individual groups are away from a global value, and that's this value here, how far the individual groups are away from a global value on average, and how skinny they are on average. There's each observation away from its own mean, which is an individual variance for all the groups. So this is another measure, and then the ratio of these two measures together. If f is big, they're separated and they're not overlapped by much. If f is small, they could be really tight together with big overlap, if that makes sense. And then the other two possibilities. Okay. But effectively, we said that when we do an analysis of variance, there's just one alpha rate, and we set the alpha at 5%. Okay, which is better than the situation when we have the three group scenario, when the error rate over doing all individual t-tests is actually 14% and not 5%. In the four group scenario, we're up to 26% and not 5%, if that makes sense. Okay. So what I'd like to do now next is, well, maybe I'll just ask you guys, are you still with me? Okay. You can, as I said, you can rewind this. Maybe what I need to actually do now is to do an actual ANOVA calculation. Okay. If that makes sense. Okay. So I'm actually going to do an ANOVA calculation, and I'm going to just fictitiously just create three groups and run through the calculation. So we're going to do an ANOVA example. Okay. And let's say we have three groups. Let's say age groups to 20 to 30-year-olds. Let's say the 30 to 40-year-olds. And let's say the 40 to 50-year-olds. Okay. So we have three groups. And what I'm going to do with the three groups is I'm going to ask the members of the groups individual questions. And the question is, how much did you spend over the weekend? The 20 to 30-year-olds, the first person spent 50 euros, the next person spent 70 euros, the next person spent, let's say, 85 euros, the next person 65 euros. The 30 to 40-year-olds spent, let's say, 120 euros, 110 euros, let's say 100 euros, and let's say 105 euros. And the 40 to 50-year-olds, let's say, for argument's sake, that the first one spent 90 euros, 95 euros, 110 euros, let's say 130 euros, and 140 euros. So it's not a balanced design because we have more observations in the third group. Okay, but what we'd like to be able to figure out is we'd like to figure out the hypothesis that we're going to try to test for. The hypothesis, okay, it has a null position and has an alternative, and we'd like to be able to figure out, is there evidence to suggest that the average of the first group is different to the average of the second group, which is different to the average of the third group, or that some pairing of these are different to each other. That's the alternative. That's what we want to try to find out, is whether these averages of these groups are different to each other. We won't know which one it is. The F-test will just tell us whether within the possible pairings, whether one of the groups is different. Okay, we'll follow it up by what's known as a post hoc test if there is a difference. So the null position is we're going to assume that there's no difference. In other words, that mu for group 1 is equal to mu for group 2, which is equal to mu of group 3. Excuse me. That's step 1, is our hypothesis. Okay. Step 2, what we're going to calculate, well, it's our significance of our test. What are we willing to accept in relation to committing a type 1 error, which means rejecting H0 in favor of HA, when actually H0 is actually true and we shouldn't have rejected it. Okay. So, well, we're going to just set alpha is equal to 5%. Okay. That's usually what we set it as. It depends. It's subjective. We're not going to kill anybody here, okay, by saying that their spending behavior is different. Okay. But let's say the social sciences, it's typically let's say 5%. If you're in an exam, they might tell you an actual significance level to set your experiment at, or based on the scenario, you might just say, there's a drugs trial. If we get things wrong, it could be catastrophic. So your significance might need to be a lot lower than that. But now step 3 in our process is to calculate the test statistic. And the test statistic in this case is an F statistic, which, as I said earlier on, it's two measures. It's a mean sum of squares between measure divided by divided by a mean sum of squares within measure. Okay, where, and I'm just going to write these down separately. Okay, where the mean sum of squares, excuse me, between measure. Okay, where the mean sum of squares between measure is equal to how far the average of each distribution is away from the global distribution squared, times we have to compensate for how many values there are in the distributions, and it's for all of the groups. Okay, do that for all the groups, divided by the number of groups we have minus 1. Okay, and the mean sum of squares within measure, the mean sum of squares within measure is equal to it's how far the individual observations are away from their own group mean squared, and we do that for all of our groups, and that's divided by, on average, n total number of observations that we have minus the number of groups. Okay, so I think what we should do first of all is we should calculate these individual group means. Yeah, so let's just calculate our individual x bars, yeah, or x bar small g's. Okay, so that's what we're going to calculate first of all. Okay, which effectively means that what we need to do is we need to add up all the observations. So 50 plus 70 plus 85 plus 65. Okay, gives us 270 in this case, and we need to divide by how many observations there are. In this case, n is equal to 4, so we need to divide that. The sample size here, the actual n, okay, the n here is equal to 4, 1, 2, 3, 4, so divided by 4, which is going to give us an average here of 67.5. Then we do this situation here. We're going to calculate the x bar small g for the second group, which is 120 plus 110 plus 100 plus 105. Okay, and we're going to divide that by 4 to calculate its average, which gives us an average of 108.75. Okay, and then we're going to do group 3, which is the 40 to 50-year-olds. We have 90 plus 95 plus 110 plus 130, 130 plus 140, and we're going to, that gives us 565, and we're going to divide that by 5. Okay, so we divide it by 5, we end up with 113. Okay, so we have all of the individual group means now, and we need to calculate this global mean, which is effectively we need to add up all of these values and divide by 4, and 4 is 8, and 5 gives us divide by 13. Okay, so the global mean, let's say x bar big G, is the sum of all these observations. Look, I should have, let's say, if I reverse this, 67.5 multiplied by 4, that's the sum of them, that's 270, plus the next one is 108.75. Oh, not divided. Second function, delete that. Okay, delete, multiplied by. Okay, actually, let me do that again. So we have 67.5 multiplied by 4 gives us 270 is there. Plus here we have, what is it, 100, 200, 300, 400, 435. So plus 435. Okay, plus what we've got here, 100, 200, 300, 400, 470, 470, 470, 560, 565, if I'm not mistaken, 565. Okay, gives us a total of 1,270. So the sum of all of these values, yeah, okay, is 1,270. Okay, okay. So I'm calculating this x bar of G, which is 1270 divided by, well, how many observations? We have 8, 8, and 5. So we have 4, 4, and 5, which gives us 13 observations. So we end up in x bar of G, divide that by 13, gives us a value of 97.69. Yeah, so let's say 97.69 to 2 decimals. Okay. So what we need to calculate first now, so now we know this, we know the group sizes. This group size is 4, so n of G here, group size, let's just say here, is 4, 4, and 5. Okay, that's n of G. We have the individual x bars. We have the global mean. So we can actually calculate this, and we know how many groups there is. There's 1, 2, 3 groups. So actually this works out to be, for the first group size, which is 4, times its mean, which is 67.5, minus the global mean, which is 97.69, which needs to be squared, plus, for the next value, it's 4 times its mean, which is 108.75, minus the global mean, which is 97.69, to be squared, plus, and for the final group, okay, its size is 5 times its global mean, sorry, its mean value, which is 113, minus the global mean, which is 97.69 to be squared. And that all needs to be divided by k minus 1, which is 3 minus 1. And that gives us our mean sum of squares between measure. Okay, so let's just ignore this thing here now for a moment. Yeah, okay, so we're just going to ignore this here for a moment. So now we end up with our mean sum of squares between measure is equal to, well, this is a bit of calculator work here. Okay, so we have it's 4 times 67.5 minus 97.69 to be squared. Okay, gives us a value of 3,645 plus. Okay, we're going to have it's 4. Let's do that again, right? Okay, so we have uh, it's let's do the middle bit. It's 67.5 minus 97.69. Okay, we're going to square that. Okay, and we're going to multiply that by the sample size for that group, which is 4, which gives us 3,645. Then we're going to add on to that. Okay, so I'm going to do this all in brackets. Yeah, okay, it's 4 times 108.75 minus 97.69. Okay, which needs to be squared. Oh, second function, delete that. Right, right. That needs to be the second function, delete. So if I'm not mistaken, that should be deleted now. Yeah. So I need to square that. So let's get squared. Okay. I'll keep making the names of this. Yeah. Sorry, guys. Yeah. If you just bear with me here. Yeah. I should. So I have a question there. Hi, Jonathan. This is very helpful. Current calculator position, bottom right of bottom right of page is good. Okay. Okay. Good. Yeah. If in other locations the light source can reflect off the calculator screen. Uh, KG, okay, thank you. I'll do this again here, yeah, okay. So maybe what I'm going to do is I'm just going to, you can see I'm making a few mistakes doing the calculator here, probably just under a little bit of pressure there. So let me just do each one of these individually, yeah. So it's 4 times, we have 67.5 minus 97.69, okay, which needs to be squared. So what we end up with here is this number here is 3645.74 plus the next one, okay, is 4 times, we have 108.75 minus 97.69, okay, to be squared. That gives us a value of 489, so that's 489.29, okay, plus the third value here is 5 times 113 minus 97.69, okay, which needs to be squared, which gives us a value of 1171.98. Sorry, I had to move that up there, kg, for a moment, yeah, okay, 1171.98. And now this all needs to be divided by 3k minus 1, which is 3 minus 1, which is divided by 2, okay. So now we can actually do this whole calculation here, which is, so now I'm doing, it's, let me fold this page over and move this page over a little bit here, okay. So now what we end up with is, we end up with, doing this calculation here, it's 3645.74 plus it's 489.29 plus 1171.98, okay. That gives us a total numerator of 5,307.01, which needs to be divided by 2. So we divide that by 2 now, and we get the numerator is 2653. So effectively now what we have is we have our mean sum of squares. Our mean sum of squares between measure is, get the calculator up here, is 2653. Is 2653.51 to 2 decimal places. Okay? So that's that guy calculated. Okay? The next thing is probably a little bit easier because it's just variance calculations. Okay, so what we need to do is for each of the groups, okay, the mean sum of squares within measure now is for each of our groups. Let me just do our 3 groups out here. Okay. So for each of our 3 groups, we need to calculate x minus the group mean squared. So we need to take the group mean away from each observation, and we need to square them. Okay, so this will be for the first group. Let's say this is A, B, C. So this will be for the first group. So let's just do the first group. So the first observation is 50. its group mean is 67.5. So 50 minus 67.5 gives us minus 17.5, which needs to be squared, which gives us a value of, actually I should have put that in brackets, yeah, which gives a value of 306.25. 306.25. It doesn't matter whether they're negative or positive, yeah, with the square will always be positive, yeah. Okay. So then we have 70 minus 67.5 gives us 2.5, which needs to be squared, which gives us a value of 6.25. Then we have 85. 85 is the x minus the group mean, which is 67.5. So we have 85 minus 67.5 gives us a value of 17.5, which needs to be squared, which gives us a value of 306.25. Okay, 306.25. And then we have 65 minus 67.5 gives us minus 2.5, and minus 2.5 squared is going to be 6.25. Okay, so we've got those squared distances for group 1. Okay, and we have to do this for all of the groups. For all of our groups, we need to calculate this. So for the second group, we need to calculate the distance that its observations are away from its mean. Okay, and we need to square them. So for each one of these observations, we're going to take away 108.75 and square it. So the first one is 120 minus 108.75, which gives us a value of 11.25. And when we square that, we end up with a value of 126.56. 126.56. The next one is 110 minus 108.75. And when we square that, we end up with a value of 1.56. So 1.56. The next is 100 minus 108.75, which is 8.75, which needs to be squared, which gives us a value of 76.56. Okay. And then finally, we have 105 minus 108.75, which gives us 3.75, which needs to be squared, which gives us 14.06. Okay. So that's the second group's square distances done. Yeah. Okay. And we're going to do sums of squares now in a moment. And then for the third group, each observation, now there's 5 observations here, and we have to take away 113. Okay, so 90 minus 113 is going to give us minus 23. So 23 squared is going to give us a value of 529. So this is for x minus x bar g squared for the third group C. This is for group A, group B, group B, group C. Okay, so we have 529 for the first one. Okay, then we have 95 minus 113 is going to give us a value of 18, and 18 squared is going to give us a value of 324. Okay. Then we have 110 minus 114 is going to give us minus 3, and minus 3 squared is going to be 9. Then we have 130 minus 113, yeah, which is going to give us 17, and 17 squared is going to be 289. And then finally, we have our 140, okay, minus 114 is going to give us 27, and 27 squared is going to give us a value of 729. Okay? So what it's saying here is that we need to sum up all of those square distances. So we need to sum up all of these values here. So let's just sum up each column. So we have 306.25 plus 6.25 plus 306.25 plus 6.25 gives us the sum of squares for group A is 625. For the next group is 126.56 plus 1.56 plus 76.56 plus 14.06, which gives us a value of 218.74. And then the final group we have 529 plus 324 plus 9 plus 289 plus 729 gives us a value of 1880. Okay? So our mean, I'm just going to go over here now. Okay? Our mean sum of squares within measure, okay, how skinny the distributions are. Our mean sum of squares within measure is the sum of the squared distances, the sum of the squared distances for each one of our groups, which is effectively the sum of squares for each of our groups, which is 625 plus. The next one is 218, 218.74 plus 1880 divided by the total number of observations that we have is 4, 4, and 5 gives us 13, minus the number of groups, which is 3. So now we end up where our mean sum of squares within measure is going to be, 625 plus 218.74 plus 1880. Okay, that gives us a value of 2,2723.74 divided by 10, which gives us our mean sum of squares within measure is 272.37. Okay, when we round to 2 decimals. So what we wanted to calculate was this F statistic. Okay, so the F statistic is the ratio of the between measure to the within measure. So now we end up with our F statistic is equal to it's equal to the between measure, which is 2653.51 divided by 272.37, which is equal to, when we do that, okay, 2653.51 divided by 272.37, okay, gives us a value of 9.74. 9.74. And remember them T statistics in relation to where you really need to be. 1.69, depending on the significance and whether it's a 1 or 2 tail test, we're up around 2 or 3 is a lot of evidence for there being a difference. Excuse me. So from a hypothesis perspective, we've set out the hypothesis. The null position is we assume all the means to be the same. The alternative is, it's just written like this, means that at least one pairing is different or they're all different. Right? The significance level is 5%. The test statistic excuse me, requires us to calculate two things: the mean sum of squares between, the mean sum of squares within. That's what we went through in this calculation here, albeit it's a bit muddy. I might send you to the actual video on how to do an ANOVA calculation, which I have in the hypothesis testing playlist. Okay? So the next step now is, the next step is to set the critical values on our curve. So step four is our critical values. Okay? Now, this is modeled on an F distribution. Now, an F distribution has two things that determine its shape. It has the degrees of freedom associated with the numerator, and it has the degrees of freedom associated with the denominator. In other words, how many observations are in each group determines the shape of this distribution. Excuse me. So it's an F distribution, and an F distribution it looks something like this. It's a positively skewed distribution, and depending on the sample sizes in the numerator and the denominator, it changes shape. Okay. Now, the key thing to keep in mind in relation to an ANOVA, you have no choice in which way you put these in. Okay, so effectively, this is a one-tail test. Okay, it's a right. This is a right tail test. Okay, so we always put all of our alpha into the right tail. So over here, we're going to put our alpha, which is equal to 0.05. Okay, so now the question is, for an F distribution, okay, with so many degrees of freedom in the numerator and so many degrees of freedom in the denominator, and with 5% of the area to the right hand in the right hand tail, what is this critical value? Okay, and we've got a set of tables that allows us to look up those critical values. Okay? So the tables are the F distribution tables. So we've got these tables that we've provided to our students. Okay? You can get them on. You can't get these ones online unless you're an NCI student. Okay? But you can get them on our Moodle page, yeah. Okay, on the maths and stats page, yeah. They're there. You can also ask your lecturer here in NCI for a copy of them, yeah. And if he hasn't got a copy from the contact Jonathan Lambert with Maths Development, I can give him lots of copies. I have lots of copies here. Okay, or you can drop into Jonathan Lambert as well. Drop into my office, yeah. So I'm looking for the F distribution, which happens to be down the end, and we've given you sets of tables for an F distribution that has 10% of the area in the right hand tail, which is not what we're looking for. We're looking for the one that has 5% of the area in the right hand tail. So it says this is a table of the F distribution. You can't really see this. for critical values for right-hand tail area is equal to 0.05. That's how much we've put in here. Right? Now, the degrees of freedom that our tables now. So our table, right? Our table looks something like this. Okay, so here's our table now. And we have our degrees of freedom in our numerator here, which is going to be the sample size. It's going to be, our numerator was our between measure. Okay? Our numerator is our between measure. So it's k minus 1. It's the number of groups minus 1. So it's k minus 1. In that case, 3 groups minus 1 gives us 2. The degrees of freedom in the denominator, okay? Well, the denominator was our within measure, okay, for our test statistic. The within measure has n minus k, okay? It's a total number of observations, which we said is 13, minus k, which is 3 groups. 13 minus 3 gives us 10. So we're 10 here now. And what we're going to do is we're going to triangulate in on them tables under the column 2 and down to the row 10. And what we actually get here is, you probably can't see that. And I actually need to stand up to try to get that up there a little bit better. Right? You probably still can't see it, yeah, but it says 4.10. Okay, so 4.10. So effectively, what we're saying here is that this critical value here is equal to 4.10. But hang on a minute. Hey, hang on. So our F statistic is 9.74. Okay, so there you go. Our F statistic is out here. Okay, this is F is 9.74, which is in the rejection region. Okay, see, if there was the key point is this: if there was no difference, okay, between the between and the within measure, yeah, the F statistic would be a value of 1. Okay, isn't that right? It'd be a value of 1. So we're so far away from it. Okay, if that makes sense, yeah. Okay, that's, we can sort of think about it, this as our demarcation point. Yeah, this is a 0 here. Okay, but effectively what we have is that we're 9.74 standard units away from where we should be. Yeah, okay, and actually we're beyond 4.10 standard units yet to be effectively different. So because we're in the tail, because our test statistic is in the tail, okay, okay, it's unusual. It's in an unusual region. Okay, things that are in the tail have a low probability. Yeah, okay. So under the null hypothesis, if the null is true, okay, well then we wouldn't observe this test statistic if that makes sense. But we did observe the test statistic, so that's evidence to suggest that the null actually is incorrect. So we should actually reject. So our decision, step 5, our decision for an ANOVA, clearly, in this case, our F statistic is bigger than our critical value. 9.74 is bigger than 4.10, and as such, we reject H0 in favor of HA at the 5% level of significance. And now that we've rejected, we can infer that at least one group is different to the others. Now, which one is it? Okay. Well, it's the one. It must be the 2 groups that have the means that are furthest apart. At least, okay, the 2 groups is Group A has a mean of 67.5, and Group C has a mean of 113. They're the ones that are the biggest distance away. So this F test has just shown us, or this analysis of, we found a difference between these 2 groups. 0.5. The second group at 108.75, and the other one at 114, which is probably in around there. So what I'm arguing here, and these all have distributions, yeah, these all are distributions, yeah. So what I'm arguing is, well, if we've just found a difference, okay, so what we're saying is that the difference must be at least Group A compared to Group C. It could also be this group compared to this, because they have a big difference. But the ANOVA ain't telling us that. It's telling that there is differences there. So now what we should do is we should follow this up now with individual tests of difference between 2 groups, yeah, which are known as post hoc tests, yeah, if that makes sense. I'm just looking at the time here, guys. It's just now coming up to 4 o'clock. So I think that's probably a nice place It's probably a nice place to leave this. But effectively, what we've done here is this analysis of variance. I've done three things. I've done the logic from a distribution perspective behind this analysis of variance technique. In contrast, to a two group test, okay, t-test, okay. What I've also done is I explored the probability of committing type 1 errors if we did individual t-tests, and in particular showed, I believe that we showed that error rate explodes. Yeah, okay, it gets a lot bigger. Okay, and then the argument was that this ANOVA is a test, it's a single test. Okay, it's a test of the difference between two variances, effectively. Okay. Okay. But the variances are dependent on the mean value, so hence this is a test of the difference between centers of distributions. Yeah, and this is just a single test, but has a single alpha value, and so this is us controlling for type 1 error rates. Okay, and what we did third was we ran through an example where we had three groups. We set the hypothesis. The null position is always that there's no difference in the centers, in the means. The alternative is that there's difference somewhere. We set the significance. We calculate the test statistic. We also then calculate the critical values. We said just keep in mind that the ANOVA is always a single tail test, and it's a right tail test. That's really, really important for us. It's always a single tail test. In other words, all your alpha goes in over here. You can do an F test. You can also do an F test to test for the difference between two variances. Yeah. Okay. And you could hypothesize that one variance is bigger than the other, okay, or one is smaller than the other, okay, in which case you have either a left tail or a right tail test. Variances are also modeled using an F statistic, okay. But anyway, that's really me done. So guys, I hope that this was in some way helpful. And I hope it was intuitive, and more importantly, I do hope that was helpful for you. And thanks for watching. Okay, and hope to see you around the college soon. Okay, so thank you, guys. Is there any questions there? Is there any questions there, guys? Thanks, KG. Hopefully everybody's okay with that. Okay. You can always go back to the stream and actually just rewind the stream and consider the stream. Maybe reflect over what I've done here later on. Okay. Okay, guys, I'm just going to hit end now. Thanks very much for the 10-14 people that came along today to tune in to this live stream. Okay, thank you. Bye bye.